Hello everybody, studying A-level maths for year 13. You've made it, congratulations, to the final video of a mammoth chapter of differentiation. It's the second biggest chapter in the whole A-level course, second only to integration, which will be coming up very soon as well. So by now we should hopefully be fairly familiar with the differentiation concepts and some new identities. Some are obviously given to us in the formula book, but the more we remember and the more we use them, obviously the better. So using what we know already, attempt these warm-up questions if you will. So here they are. There's three, I've not bothered with number 4, all about finding derivatives essentially. Question 3 is quite a challenge, so I've included a hint there if needed in the italics. So once you've had a go, press play and see if your solutions match mine. So here we go, let's have a look now at the solution to warm-up question 1. Question 1, we have to differentiate with respect to x the natural log of x squared plus 3x plus 5. And so I'm just going to call this y. So if I just say let y equal that, then I can find the derivative by doing dy by dx. Now this of course is a function within a function. So we can use a chain rule if we want to. We can say it's dy by du times du by dx. So we just need to define our u. I've done this back to front really. Technically define u first. So if I just call y equals ln of this and call that equals ln u, essentially where u is that quadratic, where u is x squared plus 3x plus 5. Okay, so the du by dx we can now work out because we've defined what u is. So the next step, so dy by du. So if I were to differentiate y, which is ln u, with respect to u, the natural log differentiates to its own reciprocal. So ln u would go to 1 over u. And then du by dx. I've got u here. So if I just take that and work out the derivative of u with respect to x, x squared differentiates of course to 2x, and 3x differentiates to 3, and the constant term will disappear. So therefore du by dx is just 2x plus 3. All that obviously in brackets of course. So that'll give us 2x plus 3 all over u, and then if we just recall what u actually was, we can piece this back in. Of course u is x squared plus 3x plus 5, so just pop that back in, we have our solution. So the derivative is 2x plus 3 all over x squared plus 3x plus 5. And if you note here that the derivative of the denominator is on the numerator, so that is not a coincidence at all when we differentiate the natural log. So this will make more sense when we come to integration as well. So that's worked example 1 polished off. Worked example 2, differentiate with respect to x, cosine x over x squared. So this is a quotient. So again, if I just let y equal this one here, then we can define this using the quotient rule, which I'll just remind you of here. So the quotient rule says if you have a function y, then the derivative of y with respect to x is v u dashed minus uv dashed all over v squared. And that is if y is a function u over v. So here, of course, we can see our u, we can define as cosine x, and our v function is x squared. I'll just put this into a little box so it doesn't get in the way, like so, just there to remind us in this next step when we actually compute it. I would always suggest to write down u and v separately. So even though you know what they are, just write down here, u is cosine x, and just write next door, v equals x squared. Underneath each, we can then find the derivative. So if we differentiate the cosine of x, we need to remember that goes to minus sine of x. And of course, if v is x squared, the derivative of that, v dashed, will just simply be 2x. So there we have cosine x, and of course x squared. And then if we, whoops, I'll change the colour of that, that'll annoy me otherwise. Sorry, seems rather pointless, but green is green, isn't it? So there we go. So now what we're going to do is apply this rule here. So the quotient rule tells us that the derivative dy by dx will be the first function, which is x squared. It's going to be a fraction, so let's get a fraction line nice and ready. So v is simply x squared multiplied by u dashed. So u dashed, we can see here, is actually negative sine x. So it's going to be x squared, which of course was our v, multiplied by u dashed, which is negative sine x. Then minus the function u. Well, our function u, of course, is cosine x. So we're going to do cosine x multiplied with what v dashed is. And so v dashed, I've not made my fraction line long enough, a common mistake of mine. We can see from this formula here that v dashed is just 2x. It's minus cos x times 2x. So all we're actually doing is essentially cross multiplication of this 4 terms here. So we do v u dashed first. So first of all, that one times that one, then minus cosine x multiplied by 2x is all we're actually doing. And all of that, of course, is going to be divided by v squared. So it's going to be v x squared multiplied by itself, x squared all squared. So once we've got that, we're essentially done, as long as we can just neaten up the fraction now. So taking what we have here, and I would suggest we expand out, we're going to have x squared minus, rather, x squared sine x minus 2x cosine x, all divided by x to the power 4. Now, because x is common with both terms in the numerator and x is only in the denominator, we can actually simplify by dividing through by x. And so simplifying by dividing both numerator and denominator by x, essentially cancelling, if you like, that's going to give us minus 1x sine x minus now simply just 2 cos x, because that x is cancelled with one of the x's here. So cancelling one of these 4 x's will leave us with x cubed. And so that's the second one sorted. Let's have a look at the final warm-up question 3. So question 3. Given that x equals sec squared of 2y and that y is defined between 0 and pi over 4 exclusive, show that dy by dx is 1 over 4x multiplied by the root of x minus 1. So I've got a couple of hints here really. So remember, dy by dx can be found by finding dx by dy first, then reciprocating that, and also a sketch of a right-angled triangle to relate sec 2y to what x is, and the other trig ratios might be useful. So we're going to use both of those hints now. So first of all, the thing to notice here is that x is given not in terms of, x is given in terms of y, not y in terms of x. And also, x is given as a function of a function. So it's sec of 2y, not on its own, but sec squared 2y, which means sec 2y, obviously all squared. So essentially, in my mind, this is a chain rule question. So what I'm going to say here is to allow x to equal u squared, where I'm saying u is sec of 2y. So if we make that our starting point, then what we can do now is to find dx by dy. So we're not finding dy by dx, but simply dx by dy. And so that's going to be differentiating x with respect to u, and then finding what du is differentiated with respect to y. So we can do this now, because if x is u squared, then if I differentiate this with respect to u, that'll just be 2u. And the second component, finding du with respect to y, we need to recall a standard result of differentiation. If we differentiate sec of kx, what that gives us is 2 lots of sec kx tan kx, where k is a constant, if there is one. And so differentiating that with respect to y, the 2 is essentially going to pop to the front, if you like, and we're going to have then simply sec of 2y multiplied by tan of 2y. So we can now piece this together, and it's hard to see how this relates to this algebraic dy by dx, but we'll come to that in just a moment. So numerically, 2 multiplied by 2 is 4. Since u is sec 2y multiplied by another sec 2y gives us sec squared 2y, and then simply tan 2y. So moving into an area with a bit more space, this is dx by dy. So what we can say now is, so dy by dx is going to be all of this reciprocated. It's going to be 1 over all of that. So it's going to be 1 divided by, move that one to the centre, oops, never mind. So it's going to be 1 over 4 sec squared 2y multiplied by tan of 2y. But now, just for a moment, let's consider this right-angled triangle which I mentioned in this hint. So going back to GCSE, we have sine, cos, tan followed by a number or an expression, in this case 2y, but we can think of this as essentially the angle. So if x is, let's just think about this for a moment. So if x is sec squared of 2y, what this means is that it's 1 over cos squared of 2y. So therefore, cos squared 2y is going to be simply 1 over x. And so therefore the cosine of 2y, if I square root this side, I'll have to square root the other side. So it's going to be 1 over root x, simply put. So you might be thinking, well, is it positive or negative? Well, if y is between 0 and 45, then the cosine of 2y will range from 0 to 90, and we should know from the definitions and the properties of the graph of cosine of x, or cosine y in this case, that it will be positive for between 0 and, in fact, 90. So this here, we can just ignore the negative and just think it's definitely 1 over x. So let's put this into a right-angled triangle. So if I think of the angle being 2y, then cosine, of course, is, going back to GCSE times, is simply the adjacent divided by the hypotenuse. And so I can define here the adjacent side, this one here, as being 1, and then I can define the hypotenuse as being root x. Hence, cosine of 2y is adjacent side 1 divided by root x, which is what we have. So using Pythagoras now, we can think about an expression in terms of x for this opposite side. And so, of course, root x all squared, which is going to be x, must be 1 squared, which is 1 plus this opposite side. So if I just call that the opposite, squared, of course. So therefore, the opposite side will be x minus 1, all square rooted. So if I just sort of box this triangle off here, well, not box, but sort of bubble it off, we can now consider a few things from this sketch. So, considering a right-angled triangle, which are lazily called a rat. It's not literally a rodent rat, it's a right-angled triangle. So if cosine 2y is 1 over root x, which we've established, then of course we can find expressions for tan of 2y. So tan 2y will simply be opposite divided by adjacent, which will just be root x minus 1. And of course, sec squared 2y is going to be 1 over cos 2y squared. So that's going to be 1 over cos 2y is root x, all of that squared, which is just going to give us x. So we can use this now in this expression for what dy by dx is. And so tan of 2y, considering the right-angled triangle, will be root x minus 1, and sec squared of 2y is going to be simply x. So piecing all that together, so therefore dy by dx is going to be 1 over four lots of sec squared x, which we've shown by using this triangle is x, tan 2y, which is root of x minus 1. So quite a lot of hard work that, but it's been proven. So now we should be suitably warmed up to have a look at this new topic, which is going to be very, very briefly explained, and then practice with some worked examples. So what is this new subtopic? It is rates of change, more specifically connected rates of change. So a one-sentence explanation before we crack into it. Simply put, if you know about the chain rule, you can use the chain rule to connect rates of change in situations involving more than two variables. Essentially, as crude as this sounds, you can think of the derivatives, dy by dx or dv by dr, whatever we're talking about, think of them as fractions and chain them together, cancel numerators and denominators until you get the derivative expression you need. That'll make more sense, of course, when we use these warm-up examples. So let's get straight to it with worked example question 1. So, given that the area of a circle, a square centimetres, is related to its radius r by the formula a equals pi r squared, that should be no news to any of us, and that the rate of change of its radius in centimetres per second is given by dr by dt equals 5, find dA by dt, which is the rate of change of the area with respect to t, when the radius equals 3. So, let's just start with what we've been told. Presumably this is going to be useful. So a equals pi r squared. Okay, of course it does. And we're trying to find dA by dt. So our target is dA by dt. So what I can do here, if I know the area, I can quite easily differentiate the area with respect to r. So I could find dA by dr. Pi is just a constant, differentiate r squared becomes 2r, so that's going to be 2 pi r. So maybe I can use that. Let's see if I can. Well, dA by dr, but I don't want anything relating to r, so if that's the case, I'll need that d on the bottom to cancel the d on the top. What I do need on the bottom is a dt. So hopefully you can see here, I'm using the idea of the fraction cancelling, and I consider this r there and the r there cancelling to give dA over dt essentially. As crude and as unmathematically robustly sound as that is, it does actually work in these cases. So dA by dr, that's great, we found that fairly easily, that's just 2 pi r. So we can fill this bit in now. And dr by dt, well luckily, if you read the question carefully, we're actually told what that is. It's 5. So dA by dr, 2 pi r, multiplied by dr by dt, which we're told is 5, then that's going to give us a better relation. That gives us 10 pi multiplied by r. So dA by dt equals 10 pi r, and that's going to be, of course, in units of centimetres squared per second. But of course, we are given the specific radius, so we can actually evaluate numerically what dA by dt is, because we're told that the radius is 3. So if we sub in r being 3, so we can find dA by dt when r equals 3. That's going to be 10 pi multiplied by 3, which we can leave in terms of pi. In this case, that's going to be 30 pi centimetres squared per second. Let's try another one together. Worked example 2. This time we're told the volume of a hemisphere, V, is related to its radius by the formula V equals 2/3 pi r cubed. And the total surface area, capital S, is given by the formula pi r squared basically the new circle you get when you halve the sphere, plus 2 pi r squared, half the remaining surface area, is 3 pi r squared. Given that the rate of increase in volume in cubic centimetres per second, dV by dt is 6, find the rate of increase of its surface area, ds by dt. So again, let's use the information we're given. So we're told that the volume is 2/3 pi r cubed. So again, what we could fairly easily do from this is we could find dV by dr. So dV by dr, 2/3 pi is a constant. Differentiating r cubed gives us 3r squared. So that 3, when brought to the front and multiplied by 2/3, that 3 will cancel with the 3 we bring to the front. So we'll just essentially have 2 pi r squared. We're also told that the surface area is 3 pi r squared. So it couldn't hurt to find the derivative of that with respect to r. So ds by dr will simply be, for this one, 6 pi r. What we're wanting, though, is ds by dt. So we need to imagine a chain which we need, which will cancel, essentially, to ds over dt. So what we could do here, well, let's just think, are we told anything else? We are told dV by dt, so maybe that could be of use as well en route. So let's use dV by dt. And if that's the case, to leave us with the ds on the top, that will need to be multiplied by ds. And because I don't want anything relating to v, I need to find ds by dv. So the challenge here will be finding a link between s and v. So let's just think about how we can do that now. So again, we're not stumped yet because we know v and s here relate to r, so maybe we can use r as a middle person to link s and v together. And we can do that using the glorious chain rule. So ds by dv, let's link them together using r. So a chain for that one would be ds by dr multiplied by dr by dv. So let's see if we can hatch a plan to get these. Well, I've got ds by dr already, so that's a formality. That's fairly good. So I know that's 6 pi r. And dr by dv is going to be a reciprocal of dv by dr. So from this we can just reciprocate that and say, so dr by dv is going to be 1 over 2 pi r squared. So ds by dt we can now piece together. So it's going to be dv by dt multiplied by ds by dr multiplied by dr by dv. So sometimes you can even chain more than 2 things together. So we've got the ingredients, now it's just a case of chaining them. And dv by dt, before we forget, was actually given to us in the question as simply 6. So just put these values in and take a little bit of care. That's going to give us 6 multiplied by 6 pi r multiplied by dr by dv, which is 1 over 2 pi r squared. So that's going to give us 36 pi r on the top. On the bottom we have 2 pi r squared. So 36 over 2, that will cancel to give 18. The pi will cancel 2. 1r will cancel with one of the r squareds on the bottom, so the r squared will just become simply 1r, and so that's going to give us 18 over r. I'll underline the answer in red, actually. That seems to be my modus operandi for the final answer. So 18 over r, that is our ds by dt. So we found it. Work example 3 is about the head of a snowman. So head of a snowman, radius r centimetres, loses volume by evaporation at a rate proportional to its surface area. So let's just start with this key fact first. So it loses volume. So if it's losing volume, what we're talking about there is an expression for dv by dt. So dv by dt is essentially proportional to its surface area, which I'm going to call A. So remembering from GCSE, dv by dt will equal some constant multiplied by A. But if we think about what we're told here, we're told that this thing is losing volume. So because it's losing volume, if we define k as a positive constant, we can put this as minus k times A. So if I just define where k is a positive constant, so we've been told that for a reason, we would presume. So that might be used later on. Let's read on with the question. So we're going to assume the head of a snowman is spherical and its volume is therefore 4/3 pi capital R cubed, because we're talking in terms of capital R, because that's the head of a snowman. Maybe its name is Robert, or maybe it's Rosie or something, so R for respect. And the surface area of it is 4 pi capital R squared. So we need a differential equation for the rate of change of the radius of the snowman's head. So what our target is essentially we want the rate of change of snowman's head, which is dr by dt. So what we need to do here is to imagine a chain which will give us that. To find such a chain, let's just again read the question and find the information that's presented to us. So we're told here, for example, the volume of a sphere is 4/3 pi capital R cubed, where R is that snowman's head's radius. And we're also told that the surface area is 4 pi capital R squared. So presumably these are going to be useful. So let's use these to our advantage. So if V is 4/3 pi R cubed, then differentiate V with respect to R. The 3 would come to the front, multiply the 4/3, which would just give us 4. Then the capital R loses a power by 1, so it becomes 4 pi R squared. And if you notice, of course, that is the same as the surface area, which is A. And if I think about A, which is 4 pi R squared, then dA by dr would simply be 8 pi R. So can we use these to our advantage to find dr by dt? Well, we need to have a dt on the bottom. The only thing that we have so far we found in respect to time is this dv by dt here from the first line. So I'm going to say that's the same as dv by dt. And of course, I don't want v anywhere mentioned, so I could do with having an expression with dv on the bottom next, so they can cancel. And I want a dr on the top. Now, I don't know what dr over dv is, but I have just worked out dv by dr. So if we remember, we can just find dr by dv by reciprocating this. So dr by dv will be 1 over dv by dr, which is 1 over 4 pi R squared. So if we just infill that piece of information now, that dr by dv is 1 over 4 pi squared, 1 over 4 pi capital R squared rather, then dv by dt I can say now is minus ka times dr by dv, which is obviously 1 over 4 pi R squared. But if we just remember that 4 pi R squared is A, we can use this in a moment to actually simplify further. So that's minus Ka multiplied by 1 over A, because that is the surface area. So therefore, to summarise, these A's will cancel. dr by dt is simply minus K, that constant we introduced early on in the question. Let's have a look at one more to finish off. So, question 4, which I've pulled from an older exam paper, an older spec one. We're told at time t seconds, the length of the side of a cube is x cm, the surface area is capital S cm squared, and the volume of it is capital V cm cubed. The surface area of a cube, we're told, is increasing at a constant rate of 8 centimeters squared per second. So we can actually put this into a derivative form. So that's just telling us essentially that ds by dt equals 8. So for part A, we need to show that dx by dt is k over x, where k is some constant to be found. And then we need to show that dv by dt is 2v to the 1/3. So let's first of all just start with what s is. So just remembering some basics about a cube here, really. The length of the side of a cube, we're told, is x. If that's the case, then of course the height will be x and the depth will be x. So the surface area of the cube, S, is going to be each surface, which is going to be x squared multiplied by 6. So in other words, I can deduce that S is 6 lots of x squared, 6 faces, and each face has an area of x squared. In the same way, the volume of a cube is length times width times height. So the volume is going to be x multiplied by x multiplied by x, which is, of course, x cubed. So from each of these, I can, of course, differentiate with respect to s. So ds by dx from this one gives us 12x. And if I were to differentiate the volume with respect to x, then dv by dx is simply 3x squared. For part A, I need to work out dx by dt. So let's just think about a chain that will give us that. So of course, I want dt on the bottom. So the only thing I know so far with a dt at the bottom is ds by dt. So I'm encouraged to use that result. Of course, I want dx on the top, so I need to multiply by dx at some point. And to cancel off that ds on the top, I'll need a ds on the bottom. Seems like we're stuck, but actually if we notice here, we've got ds over dx is 12x. So from that we can conclude, using the idea that the reciprocal of the derivative, we can just simply reciprocate it like any other algebraic expression. We get that dx by ds, the reciprocal, will be 1 over 12 to the x. And so we can now use that to our advantage. We can now sub this in here. So for part A, ds by dt, of course, remember we were told that was 8. And by doing 1 over 12x, we can multiply by 1 over 12x. And so we want to show that it can be written as k over x. Now 8 times 1/12 is 8 twelfths, which simplifies to 2/3. So first of all, I'm going to write it as 2 over 3x. Then I'm going to say that's the same as 2/3 over x, i.e. k would be 2/3. For part B now, let's box off part A so I don't run into any other trouble. Part B, I'll try and do down the side here in fact. dv by dt, I need to show that's going to be 2v to the 1/3. So let's find a chain for dv by dt. So dv by dt, again, what I can use now, I can use a few other different tricks. So because I've worked out what dv by dx is, let's see if I can use that one. So dv by dx, I want a dt on the bottom, so leave that as a dt on the bottom. And then because I've just found out from part A what dx by dt is, we can use that for our part B. So because we've got that dx by dt is 2 over 3x, we can just infill this into this expression, and dv by dx we worked out from before here at the top. dv by dx is 3x squared. And so if we just infill this, we get 3x squared multiplied by 2 over 3x. So of course that 3 will cancel with that 3. So, and 1x squared here will cancel with that. And so what I'm going to be left with is just simply 2x, which I'm going to rewrite now as 2x cubed to the power 1/3, just to manipulate it, because I need to relate this to the volume and show that this is the volume to the power 1/3. So x is the same as x cubed to the power 1/3, but of course x cubed is the same as the volume. So then I just basically say that x cubed is v, so therefore we've got equals 2v to the power of 1/3. And we're done. If you really want to show there, you can just add in, if you want to, just say since v equals x cubed. I've got to write down the c and the e. Absolute madness. So now we've shown a few worked examples, hopefully you'll be a bit more confident to try some of these on your own. You'll find some brilliant questions in the book as ever. So page 263 to page 264 is exercise 9J in the blue year 2 book. Try all the questions is my suggestion. As many as you can have, all you can eat mathematical buffet. Thanks for listening and well done again for getting through this mammoth chapter. If you're stuck, you should know what to do. If you're still not sure, say again anyway. Comment on the video, email me or find me in school, and always keep going. Until next time, it's goodbye for myself.